Second set of exercises. In this first one, from now on, we're going to start working by first creating the model and then answering some questions about that model. So the first thing is telling me that the initial population of cases of COVID was 10 cases, and it grows continuously at a rate of 33% every day. So let's start writing the data. First, the initial condition is the leading coefficient is the initial population, that is 10 cases. Because we're working with a continuous growth model, remember, we're always going to work with a base E. Then, the rate is the percentage at which our model grows. In this case, it is 43%, and in decimal notation is 0.43. Because this is a growth model, the rate is positive. If this was a decay model, our rate would be negative. And that's it. So our model for COVID cases can be rewritten as a population, and T is obviously days. So the population of COVID cases at time T is leading coefficient times my base raised to the rate times T. So this is the model. We have written the model for this continuous growth problem. Now, given that model, how many cases will exist after 5 days? So what am I being asked? I'm being given a value of days, that is, I'm being given a value of T, and I'm being asked how many cases will exist. Because this model tells me the number of cases after T times, after T days, all I have to do is to plug my 5 into the T, and that's how I will know my answers. So we will have 10 e to the power of 0.43 times 5 cases of coronavirus after 5 days. Okay, if we want to simplify this, just multiply 5 times 4.43, and this is 10 times e to the power of 2. That's enough. You can do it by hand. Then, next set of exercises. Here, a capsule of water and salt is being diluted in fresh water. If the initial concentration of salt in the water is of 600 grams per liter, and it has a continuous decay of 30% per hour, let's write the model. So as always, our base is going to be always E. Now, A, my leading coefficient, is my initial population. My initial concentration in this case is 600. And then I'm being given the rate of decay, meaning that the rate has to be negative. Why? Because this is getting smaller every time, and because it is 30%, this is 0.3. So our model for concentration can be rewritten as the concentration at time t is leading coefficient times my base raised to the power of the rate, negative rate, times t. Now, once I have created my model, I can answer the following question. How many hours will it take for the concentration to be 100 grams? So, what am I being asked? How many hours? So, the problem is asking me about time. So, if I'm being asked about time, I have to have a value for this side of the equation. So, I can just have an equation in terms of t and solve for t, and that is exactly what the problem is telling me. It's asking me how many hours will it take for the concentration to be 100 grams per liter, meaning that the right side is 100 grams, and this equals 600 e to the power of 0.3 times t. So my goal is to find the hours, that is the time. So again, this is an exponential equation, and remember, exponential equations are solved using logarithms. First off, to apply any logarithm, you have to leave your exponential term alone, meaning I have to pass this 600 dividing to the other side. Then once my exponential term is completely alone, I can apply logarithms on both sides. Remember that this can be simplified as 1/6, and this is ln e of minus 0.3 times t. Now, by the power property, I can pull down the exponent from this logarithm, meaning that I have minus 0.3 t natural logarithm of e. But how much is natural logarithm of e? This is 1, because remember, ln is logarithm base e. So logarithm base e of e is 1. So this is ln of 1/6 equals minus 0.3 times t. So lastly, t is natural logarithm of 1/6 over minus 0.3. So the answer for this question is, it will take this time to have a concentration of 100 grams per liter. Next question. I have a chemical compound of 3 milligrams. So that is already telling me something. A chemical compound of 3 milligrams grows following an exponential growth model. That is also already giving me two things: my initial amount, my initial population, and my base. Now, it's telling me that it doubles its mass in 4 hours. And it's asking me to write a model for its growth. So notice it's not telling me a rate. A rate, remember, is a percentage of growth or decay. But the problem is telling me something. After 4 hours, I'm going to have the double of my original mass. If my original mass is 3, double of it is going to be, obviously, 6 milligrams. If instead of double, the problem would have said, if it triples its mass, after 4 hours, then in 4 hours, I would have 3 times my original amount. That would have been 9. Or if it quadruples its size in 4 hours, this would have been 3 times 4, 12 milligrams in 4 hours, okay? So just be careful with reading what the problem is telling me. So, if I plug this into the exponential model, that remembers it's the initial population times my base raised to the rate. The rate is an incognita. We do not know. We're going to find first the incognita. So I'm going to write it here. First, find the rate, because we don't know the rate. So the rate is an incognita, but I know something, that at 4 hours, I have a certain amount of chemical compound that is 6 grams. So at time 4, I have 6 grams. My initial data is 3. And the thing that I do not know is my rate. So to find the rate, I have this exponential equation, and it's going to be solved as usual. My incognita is in an exponent, meaning that I have to apply logarithms to pull that exponent down. And remember that to apply logarithms, first your exponential term has to be completely alone. So the first thing I'm going to do is pass the 3 dividing to the other side. So now I can apply logarithms. So this is ln 6 over 3 is 2. ln of e to the power of r4. Now that I can pull that exponent down, and this is 4r ln of e. And you already know that ln of e is 1. So this is ln of 2 over 4 equals r. So now that I have found my rate, I can write my model. So the model for this the growth of this chemical model is, I'm going to write it as mass because we're talking about mass. The mass at a certain time is leading coefficient times my base raised to the rate we just found, ln of 2 over 4 times the time. So this is the model. Now, once that I have my model, the problem is asking me another thing. Is how much milligrams will exist after 3 hours. So the problem is asking me about amounts. When? In 3 hours. So it's giving me a time value and it's asking me a mass or milligrams answer. So what I have to do is to plug the hours where the hours go and to find the milligrams. That is, in other words, I have to evaluate my model in 3. So my model evaluated in 3 is 3e to the power of ln 2 over 4 times 3. That cannot be any further simplification. So my answer is, there will be 3e ln of 2 over 4 times 3 milligrams after 3 hours. And that is my answer.